Welcome to my video on linear and angular speed along a circular path. So let's draw our circular path here. Here's our circle. It's going to have radius r, again, angle theta, and we have got some object or the edge of pretend this is a wheel, going over a certain period of time. As it rotates, it goes through an angle theta, and it goes to this distance s. So that could be like a bicycle wheel would be a common example where you've got a rate of speed of the angle changing, and here's the distance the wheel travels over this period of time, t. So those are kind of our parameters. Now we can define the linear speed. This would be like the edge of the wheel. V is equal to S over T. That's just distance divided by time. We've seen this in other physics examples or other examples. So the speed is just the distance traveled divided by the time. Now that's the linear speed. That's on the edge of the wheel. But now let's look at the angular speed. This is going to be, if we write it in terms of the amount of angle that is changing per unit time. And we're going to define that as omega. The Greek letter omega is typically associated with the angular speed. So we know omega is equal to the angle per unit time. So now we're writing an angular measure rather than a distance measure per unit time, where theta is in radians and omega, it has the units of radians, that is per unit time, whatever that might be, seconds, minutes, hours, days, years, whatever that is, whatever unit of time is. So we can write this linear speed now in terms of this. So the velocity or linear speed is equal to distance divided by time. Now we know from previous work the distance traveled is theta times the radius. So we know S is going to be r theta divided by t. We can rewrite this now, rearranging in terms, so it's r times theta over t. And then we've seen previously that we just saw that omega is equal to theta divided by time. So that's just going to be equal to r omega. So the speed written in terms of the radius is r omega. So these are some of our equations that we need to understand when we're dealing with circular motion. The speed equation is distance divided by time. The angular speed is omega, that's theta divided by t. And then here is the speed written in terms of r and omega, just combining those. Next, I want to do an example. So here's our example. So a bicycle has wheels of 28 inches in diameter. A tachometer determines the wheels are rotating at 180 revolutions per minute. Most cars have a tachometer. Bicycles typically don't. They usually just have a speedometer. But it just tells you how many revolutions per minute you're going. And so that's what we know. We know how big the wheels are, and we know how fast they're turning. But what we want to find out is we want to find the speed of the bike traveling down the road. So how fast is the bike actually going if you would have a speedometer on it and determine how fast it is going. So we know what we're given. We are given the angular speed. We're given this omega, but we're giving it in terms of revolutions per minute, so we're going to have to deal with that. But we want the linear speed. How fast is the outside of the wheel actually turning? How fast are we moving? So the first thing we're going to need to do is we're going to need to convert this RPM into radians per minute, just to get in the proper units so we can deal with it. So we're given 180, and those are rotations or revolutions per minute. Now we're going to multiply that by 1, 2 pi. That's what we do unit conversions. We just multiply by 1, but 1 written in the proper form. 2 pi radians is equal to 1 rotation. Now we see in this case that our rotations are going to cancel out. So that is going to be equal to 360, because that's 2 times 180 times pi. And that is going to be in radians per minute. So there is our angular speed in radians per minute. That's going to be our omega. So for our wheel here, we know that it's 28 inches there, so their radius is 14 inches, because it's just half of the diameter. So calculating our linear velocity is r omega, and we know it's a 14-inch wheel, the radius is, and our angular speed is 360 pi radians per minute. That is going to be 5,040 pi, and that's going to be inches per minute. Use of the radian in an actual result is not always required. So since the radians are unitless, in other words, they don't have a number associated with them like pounds or ounces or kilograms or seconds. So our final answer here, we're going to leave off the radians, and it's just going to be 5,040 pi inches per minute. So that's how far the outside of the bike rim is traveling, and how far the rider is traveling too. But now let's convert this to something that's a little more we're familiar with. So let's convert to miles per hour, because that's what our speedometer is going to read. So once again, we're going to multiply by 1, but in the proper form. So we've got 5,040 pi, and that's going to be inches per minute. That's going to be our linear speed. Now we're going to multiply by 1 again, so we're going to take 1 foot divided by 12 inches to convert it to feet. Then we need to get into miles, so it's 1 mile is equal to 5,280 feet. So let's see, we're converting now from inches. Let's see that this is going to cancel out. So our inches cancel out, and then we're going to get so we're left with our feet cancel out. So we're in miles per minute. So let's multiply by 1 again, because we know there are 60 minutes in an hour. So let's see, so our minutes just canceled out right here. So we're left with miles per hour. It's going to be our final units. Now if we put that in the calculator, we're approximately going to get 14.99, and that is going to be in miles per minute, or revolutions, miles per hour, miles per hour. So that's going to be the same thing. And that's what our speedometer would tell us. That's going to be the speed we would read in our speedometer. So that's something we want to know. Hope you got something out of this and learned a little bit about linear and rotational speed and got something out of this example. Thank you for watching.